Hello everyone, I'm Oliver Marquet, research engineer at ONERA, and I will present you today the work on data assimilation of turbulent flows with FreeFEM, performed mainly by Markus Zauner, who's a postdoctoral researcher at ONERA, hired on the ONERA project funded by the European Union under the innovative program H2020. This work has been also performed in collaboration with Vincent and Benjamin Leclaire, who are also working at ONERA and in the same department and units. So we have been recently in the last years interested by the data assimilation of complex flows, and here you have a three-dimensional wake flow behind a square cylinder, and that will be the main topic of these slides, of this talk. And this flow can be characterized by one-dimensional number, the famous Reynolds number, based here on the diameter d and the upstream uniform velocity u infinity. And it is here equal to 22,000, which makes the flow quite turbulent, in fact, in the wake of the cylinder. To obtain the snapshots and the vorticity field that is shown on the screen in the figure, we have performed, or one of our colleagues, Julien Tandois, has performed the direct numerical simulation with an in-house compressible flow solver called FastS. And clearly, you can observe in this flow many spatio-temporal scales, as for instance, the large vortex that are shed in the wake. So you have a vortex shedding that occurs as a phenomena at a frequency, a bit smaller than 1. And you have also different vortices or smaller scales, the Kelvin-Helmholtz vortices that occur in the upper and lower shear layers that separate from the leading edge of the square cylinder. And so you clearly have two here in that case, and you also have turbulent scales at higher frequencies. And you can, to obtain all of these scales, you need to perform a DNS, which is you may perform a DNS, which is quite expensive because you need to solve for all the scales. So you need to have a mesh that is fine enough to capture all of the scales, and you need to have a time steps also that allows for the resolution of the highest frequency in the flows. So there is an alternative that is quite used in the industry, which is not to use for all the to solve for all the scales, but only but to model the turbulent scales, so the finest scales, and to solve for the statistically average scales. And this is the basic principle of the Reynolds average Navier-Stokes equation, or here in this case, the unsteady Reynolds average Navier-Stokes equation. And to model the effect of the turbulent scales on the statistically average scales, you need to introduce a turbulence model. And in the following, in our case, this will be the Spectal-Almaraz model. So we have solved this Urance equation with the Spectal-Almaraz equation using the FreeFEM software. And we have, this is how we have computed the solution that is in front of you on the figure, where you see the large scale vortices that are shed in the cylinder. So clearly, the unsteady round simulations, they are able to capture the large scale vortex shedding, but not really the small scale Kelvin-Helmholtz vortices. This is quite obvious when you compare the two figures. Still, on the vortex shedding phenomena, if you compare the frequency in both cases, you see that the frequency obtained with the Urance is a bit smaller than the frequency for the DNS. And so you may argue that this frequency discrepancy is tiny, but in fact, if you observe what happens in time, you see that it leads to an unsynchronization of the Urance simulation with the DNS. And this unsynchronization leads to large error in time, as you can see at the top figure, where we have plotted for the three instants represented before, the instantaneous velocity error fields. So the difference between the Urance velocity field and the DNS velocity field. And now, if you integrate in time, if you integrate in space this error and you show its evolution as a function of time at the bottom figure, you can clearly see that during phase where it's synchronized, the error is minimal, but it can be quite strong when the two simulations are unsynchronized. So the objective of this talk is to see if we can clearly improve the Uran simulation using data assimilation. And by data here, we mean data coming from the high fidelity DNS simulation. And the improvement that we hope is to better capture the mean flow at the low frequency scales. So here, the vortex-shedding phenomena. And these are the kind of scales that should be captured by the Urans. But also we'd like to see if we can improve the ability of Urans to capture high frequency scales, and in particular here, the Kelvin-Helmholtz vortices. There are various methods in the literature to perform that kind of data assimilation. And we have mentioned here three kinds of methods, three kinds that we have also investigated in the last year. So the first one is a variational, the main kind of method is variational method. And it basically consists in minimizing functional objectives that represents error between the output of the numerical model and the data. And there's a physical contract that the output satisfies the numerical model, which are usually physical equations. And to minimize that functional objective, we play on initial or boundary condition. Problem of that method is that to minimize that, we need to obtain a gradient, because usually we use gradient-based method to perform this minimization. And this gradient is costly to obtain because it needs to, well, if we have many inputs in the initial or boundary condition, you need to use adjoint equation. And so to obtain the gradient, you will need to perform one simulation, forward simulation, and one backward formulation. And so this kind of methods are quite costly. Techniques that can be used to reduce the cost of this method are ensemble-based method, and Vincent used that kind of method during his PhD. And let's say that, in fact, briefly, you minimize the same kind of functional objective, but now in the ensemble space. And so the cost of the method will scale linearly with the dimension of the ensemble space. But to obtain good performance, we may need a large ensemble space. So this kind of method can be also quite costly. And so here, recently, we have decided to use this last method called nudging, which consists, in fact, to introduce a feedback term in the governing equations, and so as to control its evolution towards the data. And so it seems that kind of method are quite inexpensive. And for instance, they have been recently applied to the homogeneous isotropic turbulence by DeLeoni, as shown in the figure. So to go a bit more in details into the into the equations, I've shown here the unsteady Reynolds average Navier-Stokes equation with the Navier-Stokes equation written with a Boussinesq hypothesis. So Q here is a variable vector gathering the average velocity field, or statistically average velocity field and pressure field as well. And the residual depends. So RNS is the residual of the Navier-Stokes equation, and depends on Q and Ut, when Ut is a turbulent eddy viscosity variable, which satisfies the Spalart-Almaraz model written briefly with the residual of the Spalart model in our case. So in the Nudge-Urans equation, you introduce a feedback light term in the Navier-Stokes equation only. And this feedback light term is proportional to the difference between UM, the data, and HM, the Q, the vector, the measurement of the solution Q. So to go a bit more in details into that vector, in our case, we have decided that we will make pointwise measurements at the points shown, for instance, here with the red dots. And so UM is basically a vector that gathers all the velocity measures at those points. And this is an offline step, meaning that once you have the DNS, you can gather this vector for all the time where you want to nudge the equation. And then during an analyzed step then consists to implement the operator HM, which is the measurement operator, and when you apply that to the solution Q, you obtain a vector that gathers the velocity measured of the Urans field. Okay. And so when you compare the two, you have the error in between the output of the model, HM, the Q, and the data, UM. And then when you go back to the space of the variable, thanks to the adjoint measurement operator HM transpose, then you weight that term, that feedback term, with a nudging coefficient, with the coefficients, which is the scalar in the project here, and it gives you the strength of the feedback. So I will not go into details of the value of this alpha, but to explain, when you use large value, it means that at the points where you have the measurements, you will force the equation to be close to the data, whereas if this value and not to satisfy the model, and whereas when if you have tiny value, you will have more. You will force to at those points you will respect and you will satisfy the model. So these models have been solved numerically using the software FreeFEM. For the spatial discretization, we have used finite element method. For the Navier-Stokes equation, the velocity and the pressure are discretized with P2 and P1 elements respectively. And since the Reynolds number is quite high in our case, and we have a convection dominated flow, we need to stabilize the classical Galerkin method using, in our case, a streamlined upwind Petrov-Galerkin. For the scalar model, we have used the formulation by Crivellini to ensure positivity. And the eddy viscosity like variable of the scalar mass model is discretized with P1 element. And also we need to stabilize that equation. A typical mesh is shown on the right figure. These are triangles, unstructured mesh with triangles. And here we have typically 45,000 nodes. The temporal discretization is second order, and we use a fully implicit formulation that allows to have large time steps. But to have these large time steps, we need to solve a nonlinear algebraic problem at each time iteration, temporal iteration. And this is done with a Newton method. In this Newton method, the linearization of the equation is consistent, meaning that we linearize Navier-Stokes, Spallar-Maras, as well as the SUPG term. And the resolution of the linear problem at each step of the Newton method is performed monolithically using the PETSI interface, so in parallel, both for the assembly and the LU factorization. And we use maps for the LU factorization. So I will now present the results, and typically here, these are the results of nudge Urans simulation using more or less 1,000 measurement points injected around the square cylinder, so a bit in the wake and also a bit upstream. And they are injected every time step being 0.21 here and correspond to 35 steps per shedding cycle. And clearly, when you compare the bottom figure showing the nudge Urans to the top figure showing the DNS, so at the same instance, we clearly see a synchronization effect, which is here again quite obvious when we compare to the Urans simulation, which are clearly unsynchronized. And this synchronization effect leads to a quite better frequency of the vortex shedding, which is actually the same in the nudge Urans as for the DNS. Now, this synchronization has also a strong effect on the instantaneous error. So here I show the error for the three instances, for the Urans and for the nudge Urans. And we clearly see the strong reduction that occurs not only where we have introduced measurements, but also outside in the far wake. And see, if we integrate in space the error, so everywhere in space, and we plot the evolution of this integrated error in time, we see the strong reduction obtained for the nudge Urans in red as compared to the Urans in blue. Now, we can look more carefully what happens by distinguishing the error inside the measurement area and outside. And so inside the measurement area, this is called the internal error. And again, if we integrate this internal error in space and show its evolution in time, we obtain the bottom figure, and we see that the nudge neurons, the reduction of the obtained with nudge neurons is more or less 2 orders of magnitude. So interestingly, we see that there is a residual error which is to occur in the shear layers. Now, if we go on the external error, we see that it is also reduced, but now more, not 2 orders of magnitude, but more 1 order of magnitude. So this is clearly the dominant error in the total error. Still, it's interesting. I mean, I say that this is a dominant error, but still, it's very interesting that you can achieve a reduction of the error outside of the measurements, outside of the place where you introduce the measurements. No, we have also investigated the effect of nudging sampling, and here delta S is the sampling distance. So, for instance, in the image, in the figure, delta S is equal to 1, means that the distance in between two measurements, is equal to the diameter distance, and we have observed that when we decrease this distance, we always decrease the internal error, whereas for the external error, we reach a plateau. And this is this plateau that limits in the end the reduction of the total error. And so to say the nominal case, what we have shown before is the case is indicated in the table. But it is interesting to see that the error, for instance, if you look at the delta S is equal to 0.5, so a distance in between two measurement points equal to half the diameter, you see that the total error is 8%, which is really tiny compared to the 100% of the standard neurons. So you can clearly see that you can achieve a strong reduction even with few measurements. So we also had a look on what happens on the time average quantity, and on the left you see the time average streamwise velocity of the DNS, and on the right the time average error of the neurons. And now you clearly see that for the nudge neurons, this time average error is significantly decreased. The same can be done for the fluctuation, and also, we can precisely look at what happens at the low frequency. And to do that, we have performed a spectral proper orthogonal decomposition of the different simulation of the DNS, neurons, and nudge neurons, and we have compared the results. So first, let's look at what happens on the low frequency S-pod mode, so one corresponding to the vortex shedding. And here we have shown for the DNS the 3 SPOD modes obtained for the vortex shedding at the scroll of 0.138, and the second harmonic in the middle and the third harmonic on the right. And at the bottom figure, we have shown the error of the S-pod modes between the S-pod mode of the neurons and the S-pod modes of the DNS. If you look at the same now, but for the nudge neurons, you see that again there is a strong reduction in the error. So a strong reduction now of the error at the low frequency. Still, we observe that we have a tiny residual of the error in the shear layers. So speaking about the shear layers, we have also been interested by examining the high frequency S-pod modes at scroll number more or less equal to 4. And they correspond to the Kelvin-Helmholtz vortices that I mentioned at the beginning of the talk. And interestingly, if you remember, this the neurons simulation could not capture at all the Kelvin-Helmholtz vortices. Here, we see that when the sampling distance delta S is more or less equal to the wave number of the Kelvin-Helmholtz instability, in that case 0.25, we can observe, this is the orange plot, we can observe that we start to be able to capture these instabilities, these vortices. And clearly, when we decrease the sampling distance, we can clearly better capture the vortex, Kelvin-Helmholtz vortices. So to conclude, this nudging approach is a data simulation that is quite easy to implement. It we have been surprised to see how it can improve neuron simulation with high fidelity DNS data. And I think this is the first, it's the first time that is shown this nudging approach is performed for neurons using neurons model. And we see that it gives really promising results, especially the synchronization that leads to an improvement of the time average flow and the low frequency fluctuation. But also, we have observed that we can also capture high frequency fluctuations. So the perspective of this work is to clearly use this nudging method using not high fidelity DNS data, but experimental data to see, and in particular, I would like to see if it's robust to the fact that we have noise in the measurements. And also, we like to explore what happens if we use not regular data, as we have used here in this talk, but more irregular spatial sampling, as the one obtained with particle tracking velocity symmetry. Clearly, we would like also to test that method on different flow, and for instance, on backward-facing flows that are known not to be well captured by neurons, and that exhibit a broadband spectrum. Okay, and so I will finish my talk like this, and I thank you for your attention.